In previous videos, I spent time on spherical and hyperbolic geometry, and I now want to look at Euclidean geometry. There are a few things unique to Euclidean geometry that I want to start by proving. The first one I want to start with, if parallel lines are cut by a transversal, each pair of alternate interior angles are congruent. In a previous video, I proved that if the alternate interior angles are congruent, then they're parallel, and I now want to go the other way. I'm going to assume the lines are parallel and show that those angles need to be congruent. So I drew my picture here. I have the L and M are parallel. T is a transversal. Transversal intersects these lines at points A and B, and I'm going to let C be some point on this ray over here, and F be some point on this line M over here. I then want to construct a ray, AC prime. So somewhere like this, it could be above AC or below AC. And I want to do that such that the angle C prime AB, so this angle here, is congruent to ABF, so that these alternate interior angles are congruent. The parallel postulate for Euclidean space says if I have a line and a point not on that line, there's only one line passing through that point that's parallel to the original line. So there's only one line parallel to M through A. That means this AC prime needs to be equal to L. Since I know L is parallel to M, and I've already proved if the alternate interior angles are congruent, then the lines would need to be parallel. So AC prime would also need to be parallel to M. And that's enough to give it to me. So now I know that this C prime is actually on the line L. So it's also the same as CAB. So now I have that the alternate interior angles must be congruent if the lines are parallel. The first corollary to that theorem that says if I have two parallel lines and we know they're cut by a transversal, then corresponding angles are congruent. So I know this angle here is congruent to this one here by my last theorem and the alternate interior angles. I also know that vertical angles are congruent. So now I have corresponding angles are congruent. My next corollary has two parts. The first part, two lines perpendicular to the same line are parallel. So if I have a line that is perpendicular to a given line, so we'll say these are perpendicular, well, every other line that it is also perpendicular to would create parallel lines. So in this case, all of these vertical lines are going to be parallel since they're all perpendicular. The other one says if I have two parallel lines and I have a transversal and I know that it is perpendicular to one of these two lines, then it must be perpendicular to the other. My next big theorem is the angle sum of any triangle is equal to 180 degrees. So if I have a Euclidean triangle, then I know its angle sum is 180. So let's draw this. Let's name these points A, B, C. We're going to start by drawing the line through point A that is parallel to BC. Then, by the fact that this angle here and this one here are now alternate interior angles with these two lines parallel, we know they must be congruent. So this is the same as angle B. This angle here, angle C, needs to be equivalent to this one by, once again, the fact that this is a transversal of two parallel lines. So alternate interior angles need to be congruent. And then that gives us that the angle sum, since this is B, C, and A, would need to be 180 degrees. My next big theorem is the exterior angle theorem. So this says if we have a triangle, the measure of an exterior angle of a triangle equals the sum of the measures of the two opposite interior angles. So let's suppose we have this triangle and we're going to label these angles 1, 2, 3, and 4. So what we're claiming with this theorem is that angle 4 is the same as angle 1 plus angle 2. We know that angle 1 plus angle 2 plus angle 3 is equal to 180 since we just proved the angle sum of a triangle is 180. We also know angle 3 plus angle 4 is equal to 180. So that tells me, since these are both equal to the same thing, they're equal to each other. So angle 1 plus angle 2 plus angle 3 is equal to angle 3 plus angle 4. Subtracting angle 3 from both sides gives me that angle 1 plus angle 2 is equal to angle 4, which is exactly what we needed. My next theorem, let's consider any triangle ABC. So here will be my triangle. And we'll call these A, B, and C. And I want to consider the angle bisectors. Here, about here, and then here. And where they intersect right here is point I. So here's my point I. I'm claiming that angle BIC, so this angle here, is 90 degrees plus 1/2 A. And then we have extensions for the other two of these as well. So I'm going to prove this first one, and then the other two follow very similarly. Well, we know the measure of angle BIC needs to be equal to 180 minus half the angle B minus half angle C. So this comes from the fact that this is a triangle here, so it needs to add it to be 180. And these are angle bisectors, so this is half of B and this is half of C. I'm going to rewrite this as 180 minus 1/2 times B plus C. Well, we know that angle A plus angle B plus angle C is 180, so B plus C is the same thing as 180 minus A. This gives me 180 minus 90 plus 1/2 A, which gives me the 90 plus 1/2 A that I needed. And like I said, the other two of these follow very similarly.